Dear Father in heaven, we give thanks for this day that Thou hast given to us. And we're thankful for the chance we have to learn in this setting. And we're grateful for the preparation that Dr. Tree has gone to. And pray that you please help us to be able to learn the things that He will teach us today. Pray for safety for each of us and our families. And we say this in the name of Jesus Christ.
Amen. All right. So for those who walked in a few minutes late, if you see me limping up here, I hurt myself with basketball today. So that's what's going on. I twisted my knee. So we are going to launch into the momentum equation some more today. It's probably going to take us 2 more days, is my guess. So I don't know. We have this schedule. We'll see what happens with our schedule, but I'm not too worried about that. So we started out and we talked about we're going to derive some of the transport equations, okay? And then we're going to talk about the beginnings of some solutions. Mostly in the solutions part, we're going to talk about we're going to do dimensional analysis and then use that to motivate some simplifications that we can do. And then we will talk about unidirectional flow, which will connect with our one-dimensional shell balances, and we'll see what that's about. And that's sort of as far as we'll get in solving it. Some of the simplifications that we'll talk about, that's what we'll be working on as sort of our next time around when we visit momentum equations. So we'll do this on momentum, and we'll do this on energy, and we'll do this on mass, and then we'll have an exam, okay? So that's kind of where we're going. So any questions about the sort of bigger picture here before I launch into the details? Okay, we're good. So what we were talking about last time is we started on the momentum equation and we did a shell balance on a cube. Shell balance, we did a balance of a cube and a differential cube, right? And we said, let's look at the momentum flow. You know, I guess we did momentum flux and we multiplied by the areas here. So it's delta Y, delta Z. And we looked at the momentum flow in and out of the box, okay? And we used that to come up with the differential equation, right? When we divided by the volume of the box and took the limit, right? Which is a familiar procedure. And we came up with this differential equation, which looks like the time derivative of the momentum, okay? And this is like on a per volume basis. So every time you see a row, you can kind of think mass in your brain, right? So time derivative of a change in momentum is a divergence of the momentum flux, okay? And then gravitational forces, okay? So that's as far as we got last time. We kind of had a cliffhanger, right? And we said, where are we going to go with this? So this is in a super useful form, right? Very general, but we need to expand it a little bit. So the first thing we can do is we can take our momentum flux, which we found the first day or one of the first couple of days in class, right? And we can write that out. So remember this one was P delta plus tau plus rho V. Okay, so hopefully that's starting to make a little more sense to us. We've got pressure times an identity matrix. This is the viscous stress tensor, and then this is the momentum convection tensor, right? The dyadic product here, VV. Okay, so we can take this and substitute that into there, okay, and expand that out. So I'm going to do that just on the board over here in my couple little space. So, and I'm going to write this in index notation because that'll help me with the divergence and some other stuff. I'm going to have rho VI. I'm going to have minus DI dot, and then P delta, why did I write that? I did something. Pij plus tau ij plus rho vi vj. Okay, so I took this guy and substituted in there for the dot product plus rho g, and then that's a free index, and I'm going to end up with a j. I'll call that gj. Doesn't really matter which one I pick. Maybe that's why I did that. I call that j right here. Right? The reason I'm labeling that a J is that since I'm doing the dot product, I don't need the dot here, doing the dot product, which is the repeated over the I index. Okay, and so that one isn't a vector anymore, right? That's just the sum over the i's, and so I end up with a J left. So I just want to label this J and that J as well, so I end up with only J. But it's just a free index, I can make it whatever I want. Okay, so I can write that and just expand that out a little bit. So I have this dot product between an I there, but the sum over the identity matrix is just going to give me back minus DJT. Okay, and then I'm going to have minus DI tau IJ minus DI rho BI DJ plus rho GJ. Okay, so that was really the only real simplification here is that I go from a divergence of a pressure times identity matrix and I just get grad P. Okay, so I write that out in Gibbs notation. E is equal to, and I'm going to just pull this guy out front. Del dot rho V minus grad P minus del dot tau plus rho P. Okay. So this guy is a little more useful than this other one. Okay. This one has a name. The book calls it the equation of motion. That's kind of a generic name. Okay, we'll talk about maybe in a minute what that means, equation of motion, a little bit more, but equation of motion just means it's the equivalent to Newton's second law, okay, of motion, like force equals mass times acceleration. Okay. In fluid mechanics literature, it's more commonly known as Cauchy's momentum equation. Okay. And sometimes I'll abbreviate that CME, Cauchy's momentum equation, just because it takes a long time to write out Cauchy's momentum equation. So this should have, this should mean something to us physically, right? When we stare at these terms, one of the things that I hope you get out of the class is being able to look at stuff like this and not just see symbols, but to see the physical interpretation of what those terms mean, right? So this guy, same thing, the change in momentum of our control volume. Okay. Here, this is the divergence of the convective flux, right? So that's the convective part of the flux. That's the pressure, okay? This is the shear stress. So these two terms together were the molecular, what do they call it? The combined molecular stress tensor. So that's the stresses or the momentum due to molecular motions. Okay, so the pressure ones are the isotropic terms or the normal forces, and these ones are the shear forces, okay, or the shear momentum. So they're the off diagonal ones. So when I have the x direction on the y component of momentum, that's coming into here. And then this is the body forces or gravitation. Okay. So if we think about what we want to do down here and we want to start talking about how to solve it, we look at this equation and say, how many unknowns do I have and how many equations do I have? Okay, so this is actually a set of 3 equations, right? Because it's a vector equation. So I have one equation for Vx, Vy, Vz, or the x momentum, y momentum, z momentum. And so I have 3 equations. Okay, well, I have more than 3 unknowns. So I've got velocity vectors, those are unknowns, right? So I make a list of the unknowns. I've got the velocity, that's 3. Okay. I have the pressure, that's 1. Maybe I'll put a dot. Oh, looks like a minus. Okay, that's 1. And then I have tau. Okay, and that's 9. Right? So problem. I need more equations here, right, to get rid of these. Okay, so how am I going to go about doing this? What do you think? Too early on a Monday morning? Brian's like, yeah, I bet still calling. I still have the impression still there. No thoughts? What do you think? What do we know about? How about this? Remember that I said at the beginning of these that we needed two things to be able to get useful transport equation. I said we needed a balance and a constitutive law. So what's our constitutive law here? What is that going to tell us? What do you think, Andrew?
I'm thinking Newton's law of viscosity.
Newton's law of viscosity, right? So that gives us a relationship between tau and velocities, right? So let's use that, okay? So that's what we need next. That's our next page of notes. Right? How is some relation of some function of the velocity, right? And so, that was the whole point of what we talked about in the first couple of days of class, right? Like we need some way to relate the forces here, right, on the fluxes somewhere, right? And so that's what we're getting at. So we only know one, so that's a pretty good guess. Let's see, minus mu times grad V plus grad V transpose plus 2/3 mu minus kappa times the divergence of the velocity by day. So this was Newton's law of viscosity when we have a dilatational viscosity still. That's the kappa, right? So mu and kappa here are constants. We should be able to know. All right, so what we need to do then is take this guy and plug it into here, right there, take the divergence of that. All right, so in order to get out the simplification, we need to plug that into there. Okay, so that's going to take me 1, 2, 3, 4, 5, 6 lines. Are you excited to do that? Do you want to do that on your own, or do you want me to do it on the board? I'll let you pick. We'll pick a phone. Who's like so bored, they're like, this is trivial, I can plug it in and do it out. It's fine, I can just skip those steps. Or who wants me to do it on the board? So you want me to do it on the board, raise your hand. All right, I'll do it on the board. That's more than that. Okay. Guess I didn't pull the online clips. But come to class. And you jump. Sorry, kidding. Huh? You're kind of fancy. This will be a good practice of index notation. You should all be champions of that now, right? Is that what you used on your homework, or did you not do that? You did. I guess you did all the del dot v, right, spherical coordinates. That was the homework. Okay, so I want to do del dot tau. Okay, so this is going to be di tau ij. So di. So now tau ij, I'm going to copy that guy down. So this is going to be minus mu, I have another parentheses, divj, that's the diverge or the grad v, plus djvi, right? That's transpose of grad v, plus, and then 2/3 mu minus kappa. And then this one is the divergence of v. So I have to have a repeated index. So I'm going to pick k, dk, vk. I don't want to get it confused with these I and j's. And then I have a delta ij down here. Let's see. I can put a square brace here. Okay, you follow that? That makes sense? Okay, so now we need to go through and just we need to distribute this derivative on these guys. So mu is a constant, so I can pull that out, minus mu, and then I have di vj minus mu di dj vi, right? And these derivatives, they'll be inside there. Plus, this is all a constant, 2/3 mu minus kappa. And then I have this di dk del ij. Right? Okay. So what am I saying? Oh yeah. Okay. This term, that term, they're actually the same, right? Yeah, if I do, this is the same as, I can swap the order of those derivatives. I'm totally allowed to do that. This can be dj di vi. So that one is, I call it di dk vk. But I've got a free index there and a free index there. I have a repeated index there and a repeated index there. So that's really the same thing, right? That's telling me I have del dot v. Both of those terms, that's what that is, right? So those are the same terms, so I can add them together, okay? And so the constant that's in front there can go into that guy. So I don't need to erase, do I? So I still have minus mu di dj. And this one is, let's see, minus mu, and that has a plus 2/3. So I get a minus 1/3. Let's do this. I'll just do that. Minus 1/3, and then I'll write down dj di vi. I'm going to call that one, I now have a minus kappa dj di vi. Okay, because I can call them the same thing if I want. So maybe the K's was bad choice, but that's fine.
Dr. Tree, can I ask a question?
Sure.
What happened to the delta ij at the right hand of the equation when we did that combination?
Okay, so the delta ij, I can just make that a j. Right? Remember that if I have di and delta ij,
Uh-huh.
I can just make that a delta j. Or dj.
Okay. Thank you.
The identity matrix. So I have a derivative times an identity matrix, I get back a derivative. Okay. So I can rewrite this. So we know what this one is. This is going to be minus, let's see, 1/3. Oh, I forgot the mu here. Mu plus kappa del dot v. Okay. This one here is just a derivative. That's del dot del. That's del squared. Okay. So I get minus mu grad squared v. That makes sense? You could have all done this, right? You go home and practice and make sure. Okay. So I can rewrite this now as d dt of rho v is equal to minus del dot rho v, just copying from over here, minus grad p. Now I'm going to have plus mu grad squared v plus 1/3 mu plus kappa del dot v plus rho g. So we could put a box around that one too. We're just putting boxes all over today. A long one. We'll find a way to write these a little shorter so we don't have to keep doing this all the time. But Same thing, okay, momentum equation, but now for Newtonian fluid. Okay, so this is, a momentum equation for a Newtonian. Okay, so, yes, Andrew.
Was the CME equation over here, was that for our Newtonian fluid, or was that still general?
General, right? Because I haven't said what tau is yet. So tau is general until I say tau equals this, right? That's Newton's law of viscosity, right? Newton's law of viscosity. So I plug it in here. So this is, if you remember the Navier-Stokes equation, we're getting close, right? We're not quite all the way there yet, but we're going to get there. Okay. So this term is what we got out, and that term is what we got out of tau, right? We got those two guys out. Okay. So now let's think about how many equations and unknowns I have. So I got rid of the 9, but I still have 3 equations, and I have 4 unknowns, right? Let's see, X, Y, Z momentum. Okay, I have 4 unknowns, which are P and then Vx, Vy. Okay, so we got to figure out something to do to figure out one more equation. Okay, and what we're going to need is we're going to need a mass balance. So and not a component mass balance like we're going to do in the fusion part. We need a total mass balance. And the reason for that, is intuitive, hopefully. If you think about it, not all velocity fields are going to be allowed with conservation of mass. Right? So, I can't just have, for instance, all of the velocities flowing to a single point and then just stuff disappears there, right? And, it's going to depend on what the density does too, okay? But so some combination of the density and the velocity fields, constrain what our velocities can look like, right? So we have to be careful when when we're here, we've said momentum, okay? We've said, it's Newtonian fluid and it conserves momentum, but we still have to take care of conservation of mass before we can fix this last point. Okay, so that's B here. That's the continuity. Right? So all right, so to do the continuity equation, we have to go back to our cube. Oh, bummer, we just erased it. I like lecturing in the MARB because they've got the things that go up and down. Then I can just go like, wait, and I can go back to them. Oh, okay. Let's see, so let's give our coordinate system X, Z, Y is that direction. And we're going to call that point X, Y, Z. That point X plus delta X, Y plus delta Y, Z plus delta Z. Okay. And so we're going to think now about mass flow instead of momentum flow. This one's easier, right? So the flux is more simple. Instead of having the whole flux tensor, right? We're just going to have rho Vx, okay? And then on this side it will be y. Let's see, I want this. Delta y delta z going on that side, right? Then coming out over here, it'll be rho Vx at x plus delta x, delta y, delta t. Okay, nice. This one didn't matter. And so on and so forth for all the faces. All right, so we've done this a bunch of times, so I don't want to spend a lot of time like redoing a balance here. Okay, but it's in your book, so they do this in your book, right? And you can go practice it on your own. So I am just gonna, let's see. I will skip a couple steps to this point. So all right, d rho dt is equal to minus rho Vx at x plus delta x minus rho Vx at x by delta x minus rho Vy at y plus delta y minus rho Vy evaluated at y by delta y minus rho Vz at z plus delta z minus rho Vz at z by delta z. Okay, so we can just remind ourselves of these steps. Hopefully we see where this comes from. But this guy comes from the total mass of my control volume, rho delta x, delta y, delta z. Okay, and then these terms come from these kinds of terms, right? Where I have something flowing in, something flowing out. Okay, and then I took that whole thing when I wrote it down, I divided by delta x, delta y, delta z. Okay, so that's why there's nothing there. And I remember I get the delta x here, the delta y here. Okay, so I take the limit of that one, right? So the limit of delta x goes to 0, delta y goes to 0, delta z goes to 0. And I get that yields, that's on the next page, but it's going to be the divergence, right? Of rho v. See that one? And again, d rho dt is equal to minus d dx rho vx minus d dy rho vy minus d dz of rho vz. Okay, and that's in Cartesian coordinates, but we can write it out as d rho dt minus the divergence of rho. Okay, that's the continuity. Questions about the derivation of the continuity equation? So a couple of comments. Okay. The first one is, so now we have, with this guy and that guy right there, we now have 4 equations in one, right? And in principle, if we add boundary conditions, right? So if we know boundary conditions, plus boundary conditions, okay, we should be able to solve this. And we should be able to come up with this. There's maybe one little wrinkle as well. So you notice you might have thought this, and maybe you're too tired to ask, but we may need to know, well, actually, we usually write it differently. We have a density in here, okay? And if the density varies with pressure, we might need to be careful about that. So this, we would maybe need an equation of state. Okay, if that, we have a variable density gas or something we're doing this in. So that adds another equation, but that's thermodynamics. It's easy, right? Go look it up somewhere. Okay, ideal gas is often a useful thing there, right? Okay, that one really is easy. Okay, maybe there's something a little harder. Usually you're not trying to do vapor liquid equilibrium at the same time you're doing a transport problem. Okay, unless you're doing research. But, well, all right. So that's what we could do there. Okay, the problem with this, as we'll find out, is that this equation plus that plus an equation of state plus that over there, there's no general solution. Okay, and even we're going to make an assumption here in a minute of constant density, so we don't need this anymore. Okay, this will get more simple, and that will get more simple, and that will give us the Navier-Stokes equation. And even that, no one knows how to solve analytically. Okay, there's a if you took my fluids class, I'm sure I said this at one point, but there's a mathematical prize if you can prove just the existence and uniqueness of solutions to the Navier-Stokes equation. Okay, so let's just prove that one exists, right? Not even that, what it is, right? So currently that's a hard problem. Okay, so let's do the, what happens when the density is constant. Okay, let's do that case out real quick so that we can get to the Navier-Stokes equation. Okay, so if we look at that, the continuity equation is the easiest one to do. Because what, the density is constant, that has to equal 0. Right, the left-hand side. Under any derivative of a constant 0. That's a constant. I'm allowed to pull the density out of that derivative, and then I can divide by that because it's 0 on both sides. And I can get rid of the negative sign as well. So the first thing I get is del dot V equal to 0. So this is constant density. I think I wrote it, right? Okay. So the velocity divergence is 0. So there I was, that sort of gives us maybe more physical interpretation, right, of what I said when I said that some velocity fields aren't allowed with conservation mass, right? So the divergence says basically I can't have sources or sinks. Well, that makes sense. If the density is constant, it can't pile up anywhere. I can't have a spot where the velocity just disappears at a point or it just comes out of somewhere, right? I'm just making up math. Okay, unless you're nuclear, don't talk Andrew. Okay. Okay, so then how about this guy? What happens if I take this equation and I make density constant? So I can pull rho out. So I'll write rho dv dt equals, and I can pull rho out of that one, right? Minus rho del dot vv minus grad p, that stays, plus mu grad squared v, that stays, plus, okay, now I have this whole garbage, but I have del dot v, which I just found from the continuity equation as 0. So this entire term is gone. Phew, that one was a pain to write. Okay, plus rho g. Okay, so we're almost there, but this guy can get a little easier. Let's look at that index notation. di, vi, vj. Okay, so that I can rewrite. I can just do the product rule, or the product rule, and I get vj di vi plus vi di vj. So if I go back to Gibbs notation, vj di di, that gives me del dot v plus, and this one is v dot grad v. See that, Tyler? Makes sense? Okay, so this one is also 0, right? Because I said del dot v is 0 from the continuity equation. So that one's 0 too. So now I can write rho dv dt is equal to minus rho v dot grad v minus grad p plus mu grad squared V plus rho G. All right, so that's the last one there. And depending on where you look, either this equation or this equation and that equation together are called the Navier-Stokes equation. Okay. So one thing to remember for sure, that's the two assumptions that we needed to go from our Cauchy momentum equation to the Navier-Stokes equation. Who can tell me what those two things I needed to do? Yeah.
One was constant density.
Constant density. So that's the one I just did. What was the other one? What do you think, Mark? Yeah. So what was the other thing I needed to assume? When I went from the Cauchy momentum equation, right, where I still had, I had the, we did at the very beginning of class where I plugged in the P and tau and rho VG, right? How did I go from there to here? What are the two big things I did? So Andrew said density. What was the other one? Someone help him out? Newton's law. Yeah, who said that one? That was an internet person, right? Oh, no, that was that. You sound like the internet. Anyway. Okay. It's just a mask. Okay, does that make sense? So let's make sure we remember that, right? That Cauchy, right? We had to have Newton's law of viscosity, the constitutive law, and a constant density to get to here. So if someone says, oh, solve the momentum equation and viscosity is not constant, okay, you can't jump straight to here and start putting in the variable viscosity. That doesn't work. Okay, you got to be careful. Got to go back to Cauchy and go forward again. Okay, so that's really why it's important to know about Cauchy's momentum equation. You might think, well, why don't we just get here and then we move on? And that's great, if you have a Newtonian fluid and if everything's incompressible, but you got to be able to go back and make sure. So that's an important, thing to know, right? Okay, that's it for B. Questions about this from here? Yes.
So basically the assumption made is a Newtonian fluid and the density is constant.
That's exactly right.
So what are the assumptions of Newtonian fluid? Viscosity is constant, it's not compressible.
Well, I don't think you have to assume incompressible for a Newtonian fluid, right?
Okay.
Because we have this term here in the Newtonian fluid. That's why we have the rotational or the volume viscosity, right? So Newtonian fluid we got by assuming that an isotropic fluid with a constant density. Right. So we had this. We at the beginning we said we could have this like really crummy 81 component fourth order tensor. That's a general relationship between tau and the grad v. Right? And we said, well, what do? We assumed isotropic. That put us down to 2 from 81. Those 2 were mu and kappa. Okay. And so that isotropy assumption is big, right? That means that if I shear in one direction or shear in another direction, it's the same. That makes my life easier. Great question. Other questions? You happy with Navier-Stokes? Our vectors come in to help, right? And hopefully a little bit of our practice makes it a little more comfortable writing things like this. I think if I had given you this like an undergrad, you just shuddered and run away, right? You can do that now. We've practiced. Okay. All right, let's do C. Almost done. Momentum equation and stuff's kind of hard. I feel like we have to cover like all of fluid mechanics again in 3 days. Okay, so this will take us 10 minutes. This will be good. Eulerian versus Lagrangian perspective. So this is kind of an aside. So we just derived these equations. We're going to solve them in a second. I just want to give us a quick thing to look at to help us interpret the equations we just wrote down. Okay, so the equations that we just wrote that I just erased, okay, they're written in the reference frame from a fixed observer. So if I think about like a river, okay, and let's say here's me or you standing on the river, river's edge, and we could put some Y here, okay. You know, we have some fixed reference frame. We're standing still, the fluid's flowing past us, okay. But suppose we wanted to put ourselves in a different reference frame. Suppose we wanted to put ourselves on a little boat out here, okay. Okay, and we want to see, we want to write our equations from that perspective. Okay, so this over here is an Eulerian frame of reference. This is a Lagrangian frame of reference. All right, and we the way we rewrite equations is by changing the derivatives. So if I wanted to rewrite, say, I wanted to say, take my position here, I want to say, what's my rate of change of velocity now that I'm in the boat? Okay, I'd write the total derivative of the velocity. Well, the total derivative of the velocity is, I can find by doing a chain rule. So this is going to be equal to dv dt of partials, where this is at fixed x, y, and z, plus, now I need to take the change of v with respect to x multiplied by dx dt. And this guy here should be at fixed t, y, and z. And then I'm going to have one of these for y and z as well. I'll just write them out and then we'll talk about it for a second. dv dy at fixed t x z, dy dt plus dv dz at fixed t x y dz dt. Okay, so I just wrote a chain rule and I emphasized what's constant just to help us see. So previously we were living in this world, right? We're the observer over here, and we're saying my time derivatives are at fixed x, y, and z. Okay. What we want to do is we want to move to a world where we're now moving. Okay. And in that world where we're moving, we're going to have the velocities changing in space as we move, right? As well as in time, right? So suppose like there's a rock here. Okay. We're going to have to flow around the rock. And so we want to take into account our velocity change around the rock. Maybe it slows down right here and then speeds up and then goes back to a normal speed. And we want to take that into account as we flow around the rock. Yeah.
So the Eulerian equation would just be the first term then, but Lagrangian is taking account.
That's right. So we're almost to the, so this is the Eulerian derivative right here. Okay. We're almost to the Lagrangian. We have to make one more assumption, okay, to get to the Lagrangian. So to do Lagrangian, we want to look at these guys right here. Am I right about this? Yeah, these ones right here. This one, and this one. That dx, dy, dz. Okay, and we're going to make them equal to the velocity of the fluid. So we're going to make this one vx, this one vy, this one vt. Okay, so I could, if I had a motor on my little boat, right, I could speed up and down, back and forth, okay? And these wouldn't necessarily be the same as the fluid, right? That would be whatever I wanted them to be, dictated by my motor or whatever, okay? But if I'm just floating with the fluid, if I just threw my stick in and watched it go along, that's the frame I want. So in that case, you know, I write a special notation for that kind of derivative. I put a big D. I call that big dv dt. Okay, where I have dv dt plus vx dv dx plus vy dv dy plus vz dv dt. Okay, and that's called a material derivative. or sometimes what else is it called? Oh, I'm forgetting, that's what I wrote, oh, substantial derivative. Okay, and this one, Mark's great question, okay? This is our Lagrangian perspective. Okay, so we can rewrite the Navier-Stokes equation using a material derivative, right? So when we do that, we still have, del dot V equals 0. But now, before, if you recall, I'll just write the old one up here. We had rho dv dt. I have to do this from memory. It was minus rho v dot grad v, right? Plus mu grad squared v minus grad p plus rho g. Okay, so notice that here, if I look at what this is the same thing as dv dt plus v dot grad v. Is that grad v? Yes, it is. Okay, so I have v here, right? The x, vy, vz, dotted with, so I have the derivative with respect to x, the derivative with respect to y, the derivative with respect to z, so that's the dot product there. And then I have v right there. Okay, so that is that term right there, and that term right there. And luckily there's a row in front of it. So I'm going to move that one to this side. We call this rho big dv dt is equal to minus grad p plus mu grad squared v plus rho. Okay, so that's one way that we make it faster to write. And now we can think about this equation now from a Lagrangian perspective, or think about what's happening as we're moving with the fluid. Okay, and this looks a lot like an acceleration, right? So this is like mass times acceleration, okay? And this is the sum of the forces. So in a Lagrangian perspective, what you're thinking about is some chunk of the fluid, some material element, okay? And you're thinking about what happens to this as it's moving along. So in the Eulerian perspective, you're seeing a field, right? Like you sit there, you see this thing that's moving. In the Lagrangian perspective, you're in this chunk of fluid and it's moving and deforming and doing this sort of thing, right? And what you can see from this is that the Navier-Stokes equation is Newton's equation of motion, okay? Newton's second law, force equals mass times acceleration, for that material element, right? So you have to, when you do mechanics on particles, right, you can write F equals ma down and you look at all the forces on these particles. But now for F equals ma for fluid, it's a little more wonky because this thing's deforming and doing these other things, but you can still write, the forces, some of the forces over here is the mass times acceleration. Okay. So anything else I need to say that? I think that's all I was gonna say. Okay, so that's all I have for today. Questions about this before we close? Yes.
This is like, we would call this the Navier-Stokes and Lagrangian reference.
Yeah, and so you have to be a little careful because there's this whole thing about like changing variables into, but I say perspective. Okay, just it's a way to interpret these equations from a Lagrangian perspective. Okay. All right. Thanks, guys.
Thank you.
Yeah, thank you. Thanks, Zach.